So there were 7 questions which appeared from quantum mechanics in December 2019 in your CSIR exam. So we have already discussed the first 3 questions in your first part. So in this second part, we'll be discussing the remaining 4 questions. So the first question here is the energy eigenvalues of a particle of mass m which is confined in a rigid 1D box of width L are En. Okay, meaning you have a 1D box, right? The energy eigenvalues of this box is given by En, right? So where n runs from 1, 2 and so on, and the width of the box is given by L. Okay, now let us read the other sentence of the question, which says that if the wall of the box are moved very slowly towards each other, the rate of change of the time dependent energy dE2 by dt of the first excited state is, and the options are given. Okay, it says that the walls of this box are moving towards each other, right? So with time they are gradually moving towards each other, right? So every time this wall is moving towards each other. So what we need to do is we need to find this dE2 by dt. Okay, so how do we start? We start by calculating En first. So we know for 1D box En is given by n square pi square h cut square by twice m L square, right? And from this question we see that L here is a function of time, right? Okay, so we need to find dE2 by dt. So how do we find that? So okay, so first we find E2, which is given by 2 square, right? So it is 4 pi square h cut square by twice m L square, which is equal to twice pi square h cut square by m L square. But remember here that this L is a function of t. Okay, so now finding dE2 by dt, which is given by, so it is 2 pi square h cut square by m. So these were constants, right? And then ddt of L to the power minus 2, right? Okay, so now what is this? This quantity is 2 pi square h cut square by m. So it's given by minus 2, L to the power minus 3. So I'm going to write it as divided by L cube, and dL by dt, right? So this quantity 2 pi square h cut square by m L square is nothing but E2. So E2 then minus 2 by L. So I've already taken L square in this E2, so only L remains. So dL by dt, which is given by minus 2 E2 by L dL by dt, right? So this is my dE2 by dt. And if I see in my options which is provided, so the second one, the third one is the correct option, minus twice E2 by L dL by dt. So in the second question I have 2 spin-half fermions of mass m which are confined to move in a 1D infinite potential well of width L, and if the particles are known to be in a triplet state, ground state energy of the system. So that ground state energy of the system is to be calculated. So I have again my 1D potential well, right? So where the energy eigenvalues are given by n square pi square h cut square by twice m L square, right? So and I have 2 spin-half fermions which are in the triplet state. So in the triplet state, right, I have my up and then a combination of up down in the symmetric state, and then a down state, right? Okay, so now what we need to do is we need to find the energy of the ground state for these 2 spin-half fermions. And here what we need to remember is the ground state here, because the particles, these are fermions and they will respect Pauli's exclusion principle, right? So which states that in a particular state you cannot have two fermions with same quantum state. And for the triplet states, so if we like respect the Pauli's exclusion principle, then the ground state will be given by n equals to 1 and n equals to 2, right? Hence my ground state energy is given by pi square h cut square by twice ml square into where n is 1 and 2, right? So that gives me 5 pi square h cut square by twice ml square, right? So hence the correct option is D, because I have been asked to find in units of pi square h cut square by twice ml square. So my D is the correct option. So before moving into the third problem, I would like to introduce few formulas here, which are like the spherical harmonics YLM theta phi, right? So these spherical harmonics are the eigenfunctions of your L square and Lz, and also of the angular part of your hydrogen atom, right? Okay, so which is given by some constant PLM. So this is actually only theta dependence, no phi dependence. So this PLM is your associated Legendre polynomials, and then the phi dependence is given as e to the power im phi, and we need to remember here that m is always greater than or equal to 0. So this associated Legendre polynomials can also be written in terms of your Legendre polynomials PL of x, and we need to remember few of the Legendre polynomials. So which is P0, the 0th order one is given by 1, P1 the first order is given by cos theta, and so on and so forth. So in the third question we are given a normalized wave function psi xyz, right, where n here is a normalization constant and a is some positive constant, right? So what we are asked is, if L is the angular momentum operator, then we need to find the eigenvalues of L square and Lz, right? Okay, so for that what we will do is we will try to express this xyz in terms of r, theta and phi, right? So it is given as e to the power minus a x square plus y square plus z square, right? So now what we will do is, in terms of psi, r, theta, phi, so you have n and z is your r cos theta, and this quantity here is r square, right? Okay, so now the eigenvalues of L square and Lz, right? So the eigenfunctions of L square and Lz is your YLM theta phi, which we just saw, right? So here the dependence is given by some PLM of cos theta, right, and e to the power im phi. So in this expression we see that the cos theta term here is, so YLM from this, for this wave function, is given by cos theta, and there is no im phi term. So m here is 0 phi. So that means for me, for this question given, I take my m to be 0. Now we know that this cos theta, so for P0 of cos, for P0 of cos theta you have 1, and PL of cos theta we have cos theta, right? So that means my L in this particular wave function is given by L equals to 1. So what I do now is, the eigenvalues of L square is given by L into L plus 1 h cut square. Hence from here my L is 1, so it is 1 into 1 plus 1 h cut square, which is twice h cut square, and my m, the eigenvalue of Lz is mh cut, hence it is given by 0, right? So m is 0 for me, so 0 h cut, hence 0. So the correct option here is your option C, where your L square eigenvalue is given by twice h cut square and Lz eigenvalue is given by 0. Now in my fourth question, it is similar to the third one where the wave function is given. This is in the xy plane. So, and in the in the polar coordinates, so psi of phi is given as a cos square phi. So what I need to do is I need to find the possible outcomes of measurements of z component of angular momentum Lz in this state, and we need to express it in terms of units of h cut square. So how do I do it? I need to find the measurement of Lz. That means I need to find the eigenvalues of Lz. And I know that the eigenvalues of Lz is given by mh cut, right? So similar to your third problem, what I need to do is from the wave function which is given here, so which is psi of phi, I need to express it in terms of e to the power I m phi, because I know that in my spherical harmonics, the spherical harmonics are the eigenfunctions of your L square and Lz, and the phi dependence is given by e to the power I m phi. So for this psi phi which is given, I will express it in terms of e to the power I m phi. So which is very simple. What I do is I take it as a and then e to the power I phi plus e to the power minus I phi by 2 whole square, which is given by a by 4 e to the power twice I phi plus e to the power minus twice I phi plus 2, right? Because e to the 2 into AB, which is just 1. So I will just write it as I 0 phi, which anyways is 1, right? So the possible m values here are 2. So 2 here, minus 2 here. So 2 minus 2 and then 0 here. So that means, it's 2 minus 2 and 0. So that means my eigen values of Lz, or the possible outcomes of the measurements of z component, is Lz, which is given by plus minus twice h cut and 0. So hence the correct option is your D. Do like, share and subscribe to our channel Physics. Press the bell icon to get notified about the latest updates on the channel. We will meet in the next video. Until then, keep learning and exploring physics.